All right, right now I want to look at analyzing functions. So when we analyze a function, we are going to find lots of different things in the function. We're going to look for domain, range, extrema, continuity, or discontinuities, I guess, end behavior, lots of different things. So let's just get started. Here I'm going to be analyzing this function x cubed minus 3x squared plus 3x plus 1 divided by x minus 1. The first thing that we want to do is find the domain. The domain of this function is going to be all real numbers except for the values that make the denominator 0. There's only one place where the denominator would be 0, and that's at 1, right? X minus 1 equals 0, so you get x equals 1. Okay? So the domain is going to be negative infinity to 1, and then 1 to infinity. The range, we're going to get that from the graph in a second, but from the previous video, we should know that x equals 1 is going to be a vertical asymptote. So we can fill that in right now. X equals 1 is a vertical asymptote. Right? We can go to our graphing calculator and type this in because we're going to need to do some analysis. We're going to plug in x raised to the third power minus 3x squared plus 3x plus 1, and then we're going to divide that by x minus 1. We'll hit graph. All right, so we get a pretty funky graph there. And we want to look at the range next. Okay, so the range of this function, remember, that's the y values that are included in the graph. This function is covering all y values. So if you ask yourself, is negative 3 in the range? Yes, there's graph there. What about positive 3? Yep. How about 17? Yeah, there's going to be graph up there too. Okay, so the range here is all real numbers because the graph covers all of the y values. So the range is all real numbers, or we could just write negative infinity to infinity. The y-intercept is going to occur where x equals 0, but we can just see that from the graph pretty easily. The y-intercept is at 0, negative 1. Okay. The x-intercept, that's a little bit tougher to find, but we can do that using the 0 finder on the calculator. So we will do second, calc, 0. I'm going to pick a point to the left, so maybe like negative 1. Pick a point to the right, so maybe something like 0. You can see that x-intercept is between those values, so I'll hit enter. And it tells me that the 0 is at negative 0.259, so we will put negative 0.26. And we always write these as a point, so this is 0, darn it, no, negative. So we'll write negative 0.26, comma 0. I'm going to kind of skip around here just based on what we've already found and what's easy to find first. So continuity, that just means we're looking for any places of discontinuity. We found one place where there's a break in the graph, and it is right here at 1. So it's discontinuous here because there's no graph at 1. So we'd say it's discontinuous. I'm going to abbreviate that, at x equals 1. So when it asks you for continuity, you're really going to just be listing out where is it discontinuous. Extrema, we can figure that out from the graph. We can see that there's one minimum right here, so we can go find that minimum with the graphing calculator. We'll do second calc. Minimum. I'm going to pick a point to the left of the minimum and then a point to the right. So looks like that's pretty good. And then I can see pretty clearly that 4 is to the right, so maybe I'll type in 4. Take a guess. So I get a minimum there at 2, 3. So there's one extrema and it's a minimum. So we'll write that there's a minimum and it's at 2, 3. Increasing and decreasing. So we can see that this graph, remember we're measuring from left to right. So this graph is decreasing as I move from left to right until I get to 1, then the graph breaks. So we'd say that it's decreasing from negative infinity to 1. And then you can see right here, it's falling as well right here, right? As we move from left to right, it's falling, so it's decreasing until I get to x equals 2. Okay, so we'd write that from 1 to 2 it's decreasing. You would not include 1. You could not write one interval from negative infinity to 2 because 1 is not in the domain. It's not part of the graph. So you do have to write it as 2 intervals like this. Where is the graph increasing then? So here at 2, it starts increasing, and it's going to continue increasing the further you go to the right. So we'd say that it's increasing from 2 to infinity. Does the graph have any symmetry? No. You can pretty much just look at this graph and see that there's no symmetry here. All right, whether it's point symmetry or line symmetry, there is none. All right, what about end behavior and end behavior asymptotes? Okay, so that's what I want to address last here. And so we will do that. Let's take, and we're going to look at the degree on top versus the degree on the bottom, as we talked about in the previous video. Right, these rules right here, we compare the degree of the numerator and the denominator. What I see is that the degree on top is greater than the bottom. Okay, so that means we need to divide to find the end behavior asymptote. So I'm going to take x cubed minus 3x squared plus 3x plus 1 and divide it by x minus 1. Because I'm dividing by just x minus 1, I can use synthetic division. So I'm going to write 1 in the box. List out the coefficients, 1, negative 3, 3, and 1. And divide that by, and do the division. So I'll bring down the 1. 1 times 1 is 1. Add them up. I get negative 2. 1 times negative 2 is negative 2. Add them up, I get 1. 1 times 1 is 1. Add them up, I get 2. Okay. Now, the remainder doesn't matter. Right? What's going to define the end behavior is your quotient. Okay, so our end behavior asymptote is going to be y equals, I started off as a third degree polynomial when I did division. When I divide it once, I'm going to get down to a second degree polynomial. So this will be x squared minus 2x plus 1. So x squared minus 2x plus 1. That's going to be the end behavior asymptote. I'm going to show you the graph of that soon. But first I want to address end behavior, just in general. When I look at the end behavior of this, I look to the left and to the right. The end behavior, as I track it to the right, is positive infinity. It's going up as I trace the graph to the right. As I trace the graph to the left, it's also going up to positive infinity. So we would write that the end behavior, remember there's always two parts, the right and the left. So we write the limit as x approaches infinity of f of x. So as we go to the right on the x's, what are the y values doing? They're going to positive infinity. As I go in the other direction to the left, as x approaches negative infinity of f of x, the graph is going up, so I get positive infinity. All right, the last thing that I want to do is sketch this graph. Okay, so starting off, I can sketch that there is, try to sketch the graph here. There's a vertical asymptote at 1, and we're going to put those in as dotted lines, or dashed lines. So at 1, I'm going to put in, let's see, careful, these go by halves here. So at 1, I'm going to put in that dashed line. I'm going to go to my graph here just for reference, and I know that there's a minimum at 2, 3, so I'm going to put a minimum there at 2, 3. And then, guys, I'm not super picky about plotting a bunch of points. I want the general behavior of the graph, and so if you got the minimum down there, you know that the curve goes up like this and comes up like this close to the vertical asymptote there. That's fine. If you want to plot more points from your table, then you can. I know the y-intercept is at 0, negative 1, so I'll plot that. I know that the x-intercept is in there somewhere. And I know that the graph is going to kind of bend close to the vertical asymptote there. It's going to come up going like this. Okay. And that's what I'm looking for on these. Good sketches, or rough sketches, but with the asymptotes in there, any points that you know should be plotted, and then the general behavior of the curve beyond that. All right. I'm not going to have you analyze behavior at vertical asymptotes, which is the last box here. I'm going to include it in this video just in case I teach honors someday and I need it for that. But if as in regular pre-calculus, we're not going to do this. So if you want to stop watching right now, because this is regular pre-calc, then you can stop. The behavior at the vertical asymptote here at 1, there's two kinds of behavior. What's happening by the asymptote as you approach it from the left-hand side? What happens as you approach it from the right? Okay. So as you approach the asymptote from the left, it's going down, so it's going to negative infinity. The way we write that is we say the limit as x approaches 1 from the left-hand side, that's the negative side, we just put a little negative sign there, of f of x is equal to negative infinity. Because, again, as you approach it from the left, it's going down. The limit as x approaches 1 from the right-hand side, so the positive side of f of x, as we approach the asymptote from the right, it's going up. And so we say it's approaching positive infinity. All right, and that wraps up all the components of analyzing a graph, a rational function.